Good morning, everyone. Once again, congratulations to SAEMC for putting on another great conference and for inviting us to tell you about the Copperbelt right here in South Australia, the Curnamona Copperbelt. Now, the story started about 1.6 billion years ago along the proto-eastern margin of the Australian continent, if such existed. And there was a major volcanoplutonic event that happened, and it was indirectly responsible for the generation of pretty well all of Australia's major copper deposits: Mount Isa, Ernest Henry, Olympic Dam, Carrapateena, and so on. And so you'll see that the Mount Isa Kalkaroo block and the Gawler Craton, lying in between them is the Curnamona Craton or province. And the volcanism and the plutonism occurred in the Curnamona province, just like the other provinces, so there's no reason, in our opinion, why we shouldn't find major copper deposits. Now, we know as explorers that nature seldom repeats, but it almost certainly rhymes. So the copper deposits we find in the Curnamona may not necessarily be identical to those that we find, for example, on the Gawler Craton, the classic ironstone hosted. And in fact, that is the case. And hence the Curnamona Copperbelt, or at least the Copperbelt concept. Now, there are several key things in the Curnamona province which indicate a Copperbelt type geology. Firstly, the mineralisation is strongly strata bound. We have widespread copper gold plus other multi-metal mineralisation in a particular horizon or horizons. That horizon occurs at a major redox boundary, and the whole area is folded into a series of domes and basins. There's quite low-grade metamorphism for the Curnamona. And the other characteristic features are there are ubiquitous granites that intrude these domes. There are large brittle fracture faults which seem to be the conduits for the copper mineralisation. And the metal zonation we see in the mineralisation there is very similar to what we see in porphyry systems. I'm not suggesting we have porphyry systems, but the zonation from high temperature tungsten, moly, up through copper gold, into arsenic, then lead zinc, is very reminiscent of what you see in porphyry systems. And the final point to note, which I'll illustrate in the next few slides, is that these are extremely large systems, mineralised systems. And the type example is Kalkaroo, which we've drilled 600 odd holes into, so we know a little bit about it. And I'll demonstrate the Copperbelt model with reference to Kalkaroo. So you have a footwall, hanging wall, and the mineralisation occurs between that footwall hanging wall. We call it the prospective sequence, or K2 horizon. There's a major fault which chops through, and as all good ore bodies have, a barren shear in green. And so as I said, we've drilled 600 odd holes, so we know that the mineralisation occurs mostly between the footwall and the hanging wall horizon in that prospective zone. And the primary mineralisation is very simple. It's chalcopyrite pyrite. It's a large disseminated ore body, and it's been affected by supergene enrichment weathering, which has produced various secondary mineralised zones. That resource can be put inside an open pit, and at current copper prices, it captures about 200 odd million tonnes of ore inside that conceptual open pit. And to give you an idea of the scale from one end of the pit to the other, conceptual pit, it's about 3 kilometres. So we're talking about a huge scale. And this is just another view of the Kalkaroo ore body, just showing the different the metal types or ore types. At the bottom, the blue, the steel blue grey colour, is the primary sulphide. That's the bulk of the ore body, about 75%. Then we have a chalcocite zone we've produced by weathering of the primary sulfides, the native copper, which is the pink, in saprolite, and then saprolite gold above that, which lacks native copper. So that's a supergene enriched zone superimposed on top of the primary sulfide ore body. And just another view showing that. This slide shows the north dipping strata-bound nature almost of the, you can see it in the blue primary sulfide zone there, which is basically generated from the resource block model. And it's a nice big thick ore body, 50 to 80 metres thick, with very little internal dilution. It dips down at 45 degrees to the north, and as far as we know, it goes to great depth. There's mineralisation along the fault zone, that red fault zone, and where it cuts the prospective horizon, we have the best grade mineralisation. And of course, all of that is supported by 600 odd drill holes. And you'll notice something curious about the drilling. Where the drilling stops, our resource stops. So the ore body is open both ends. It's only limited by our drilling. You'll see some of those holes on the down dip side there have red zones in them, copper, above 0.5% copper. So we have ore grade intercepts at great depth. So we know the ore body goes on down. We can't put it in a resource category because our drilling is just too sparse. So we really don't know how big the Kalkaroo ore body is. Now that you know a bit about Kalkaroo, let's put it in the regional context, and we find that because there's virtually no outcrop out there, the aeromagnetics is one of our most valuable tools for seeing what the underlying lithologies are doing. And you can see the Kalkaroo deposit there, the resource sitting there, following around like a boomerang, an arc on the northern end of a dome, and cut by a major linear feature, which is the Kalkaroo Fault, which is up to 50, 100 metres wide, a major fracture zone, brecciated. It is well mineralised, and we haven't yet drilled it out, but it's a long linear feature. So you can see that you have both the stratigraphic component, stratabound component, and the structural component there. And zooming out a bit further, you can see the Kalkaroo South Dome, as we call it, that elliptical shape there, magnetic shape with the linear fault cutting through, and then the Kalkaroo North Dome. I haven't shown on this map, but there are numerous other prospects around there, as you might expect, where there are faults and where things have come right. And this takes us right back to the first slide of the regional aeromagnetics. So we have I'm like Anthony, I can't read without my glasses, so excuse me looking at the screen. We have the Kalkaroo domes there, which I've mentioned. The Burksgate Dome, Eurinilla Dome, Burksgate Dome, to name a few. There are other domes, but they're the main ones. Each one of those are anticlinal, doubly plunging anticlinal structures with synclines in between. Down in the south we have a major granite belt, that brain texture there. It's a huge granite belt, largely unrecognised actually. There are big roof pendants of metamorphic rocks in it, but it's basically granite, and it separates the lower grade terrain that we're working in around Kalkaroo from the very high grade terrain down around Broken Hill. The redox boundary I mentioned, you can see the contrast between the higher magnetic footwall rocks, which are magnetite bearing, to the non-magnetite bearing carbonaceous shales, which form the hanging wall. And you can see that redox boundary, you can trace it around for about 300 kilometres around the region. Granites, ubiquitous granites, intruding into the middle of the domes, often in the margins of the domes. They're later than the folding, but may have ultimately had something to do with the mineralisation. So I'll give you just a little further insight by looking at a couple of examples of our regional prospects. We have many regional prospects here, but I'll briefly describe the Eurinilla Dome and the Burksgate Dome, what we've found there from our regional exploration. So the Eurinilla Dome, Typical exploration prospect, a lot of shallow air core drilling, a few deeper holes, sniffs of mineralisation. And you can see how that relates to the dome. The core of the dome is the higher magnetic zone there, it's aeromagnetic image. Beautiful dome-shaped structure, about 10 kilometres from one end to the other, and quite a lot of drill holes drilled into it. So we modelled the footwall contact, remembering that strata-bound mineralisation, the footwall contact, so anything above that is the prospective horizon. And it's not, of course, it's been planed off by erosion. It doesn't form a dome like that, but it's just for illustrative purposes. And further image there on the superimposed on the aeromagnetics, and just removing the aeromagnetics there for a moment. And this is where the story really starts to get interesting, because when we looked closely at some of the drilling, and even drilling we'd done, we got a lot of low-grade hits in some of the deeper diamond holes, sub-economic grade at those depths. But what we'd found was an exceptionally high-grade intersection there, you can see. And that was in supergene-enriched rocks. And so we continued looking at the data. BHP basically drilled all those holes up to the north, and they also got quite a supergene-enriched gold intersection in one hole. So then Bob Johnson did something very clever. He asked the age-old exploration what-if question. What if this supergene zone, which we know occurs at a certain RL below the surface because the land out there has been stable for the last 100 million years, the water table, the supergene-enriched zone is controlled by the water table. What if we just drew an RL surface around this dome, and so maybe that could be our target, where we get enriched mineralisation in the supergene zone rather than the low-grade primary mineralisation. Now, as it happened, we would love to have drilled nearer that earlier hole on the east side of the dome, but we couldn't because we didn't have a heritage survey done at the time. But we did have some heritage survey done on the the western side, about 2 kilometres as the crow flies. And so after a couple of holes not quite in the right spot, we actually snagged the supergene zone that Bob had predicted between his white lines, and we got a spectacular supergene intersection. Now the model is shown in that section. Basically you have a very shallow dipping mineralised horizon. It's low grade, maybe 0.2, 0.3% copper, 0.2 grams gold, sub-economic at those depths. But due to the supergene weathering, the metals have moved down to the supergene zone above the water table. They've concentrated in that red section there, which is between those two white lines that are drawn around the dome. And if you're smart enough to put your drill hole in the right spot, lo and behold, you get a bonanza intersection. If you drill too far to the west, say, you're way out in the hanging wall and you've got no hope. If you drill too far to the east, you've eroded off the prospective zone and you're drilling footwall. So even although it's a huge system, you've only got a sweet spot of about 100 to 150 metres width where you have to site that drill hole to hit your bonanza supergene enriched zone. And this is just another closer in view, just keeping things in perspective with the magnetics. You can see the dome there, that shape which I've got here. It's actually a model shape we did. That's our target, and there's hundreds of millions of tonne target in that. If you follow around the dome, that gives you an idea of the scale, and just their cross section there to keep in mind what we're actually looking for there. So where do we go next with our exploration? Well, we have a problem of scale. That white line, between the two white lines, which is our prospective zone sweet spot to find a supergene ore body which might be economic, it's about at least 20 kilometres long. And you wouldn't believe, unless you look very closely at that drilling data, that it could be so easily missed. The vast majority of those holes that are drilled there are totally useless in retrospect, or with the benefit of hindsight, because they're either too shallow, they're out in the hanging wall, they're up in the footwall, And when you actually look, the number of holes that went deep enough that actually hit that white horizon there, which is our target, is very, very few. And three of the best ones are the ones that I've shown you. So that's the Eurinilla Dome prospect. Burksgate prospect, another fascinating story. I call it a geological riddle, and it took us a while to figure it out. Pretty blank canvas, really. A bit of shallow air core drilling, but in a joint venture with MMG quite a few years ago, we actually hit on a magnetic target quite a nice intersection of copper, gold and moly. And in fact, MMG got very excited and they drilled 5 holes into it, so we know it's real. And if you look at the aeromagnetic, sure enough, there's a nice little magnetic anomaly there which is reflecting a banded iron formation, which is a host of the mineralisation. So, okay, there's lots of magnetic anomalies there. They drilled a few. What does one do next? Is the question. So we started to put together the structural picture. We knew that that area to the east there was a big anticlinal dome with classic football in the middle. So we were able to draw an anticlinal structure. And then we knew next door there was a big synclinal structure and usual couple of faults. So we had the basic structured architecture which matched with the aeromagnetics. So then the next thing, of course, have the courage and conviction and drill some holes. So you'll see there's 3 holes there, or a number of holes, but 3 in particular. And so we decided that we'd drill where we thought that the prospective horizon would come up nearer the surface again. And when we drilled 3 holes there, lo and behold, we hit mineralisation in all of them. And the key thing was that it had the unique geochemical signature that Burksgate, the original Burksgate intersection had. So it was copper, gold, moly, but also very distinctive levels of rare earths, certain types of rare earths, vanadium and uranium. So there's absolutely no doubt that that horizon that we got 2 kilometres to the east on the other side of the syncline is exactly the same as what we intersected at depth in the diamond drilling. So you can see the syncline there. Question is where to drill next. That's always the explorer's question. Well, we know that yellow zone, which Bob's modelled there, is about 8 to 10 square kilometres. So we have 8 to 10 square kilometres of prospective horizon that forms a great big syncline there, which is almost certainly going to have mineralisation in part of it. We know where it comes up on both sides it's mineralised, so why not in the middle? So that's one target. Then to the east, we've got that big anticlinal structure. Well, we're not going to find the mineralisation in the core of the structure unless there's a different style. But the magnetics helps us because you can see running around that anticlinal zone, we've probably got about 30 kilometres of the same prospective strike rocks, which we know from shallow air core drilling are copper anomalous. So again, as explorers, we have a problem of scale. Where do we drill the next hole? If you have good ideas, you can tell me afterwards. So that brings us right back to the start and our conclusions, which I'll have to read from the screen up here. So I hope I've convinced you the Curnamona province is highly prospective for copper-gold multi-metal discoveries, and that mineralisation is largely strata-bound. In fact, we would classify the deposits out there as structurally controlled strata-bound. Primarily strata-bound prospective horizon, but structure, as always, is super important in providing the conduits for the mineralised fluids. These are very large mineralisation and alteration systems, which I hope I've demonstrated with a couple of prospects I've shown. There's a wide range of associated potentially economic and recoverable metals, not just copper, gold, but moly, tungsten, rare earths, beryllium and uranium. And these are often in economic levels. The metallogeny is somewhat different to the Gawler craton in that sense, for example, with the cobalt. But ultimately, the source of the metals is likely to be the same. It's likely to be related to this big A-type felsic volcanoplutonic event, which, as I showed you in the first slide, ran up and down the east side of Australia at the time. And there are analogies in Australia. This is not a unique type of setting. There's two provinces I've worked in extensively in my career, and one is the Paterson. The Telfer deposit is basically a strata-bound gold deposit. Nifty, Winu, and possibly Havilah. And then the granites Tanami. The granites is a strata-bound gold deposit, and essentially Dead Bullock Soak and Kali are confined to a particular stratigraphic horizon, albeit strongly structurally disrupted. So on that note, I will finish. Thank you.